So this section we're going to talk about determine whether in a scenario if the events that are happening are independent to each other or dependent. Independent pretty much means that one event is affecting the outcome of another event. That's what dependent, I'm sorry. Dependent means one event is affecting the outcome of another event. Okay? Independent means one event does not affect the outcome of another. Okay? Maybe there's really no relation. Event A has nothing to do with event B. It's not affecting it at all. That's independent. Dependent, there is some sort of effect. Something's changing. Event A changes the outcome of event B. It's affecting it. Right? How I like to think with independent events, the probability doesn't change. Nothing changes. Everything stays the same throughout. With dependent events, the probability is changing. Okay? That's how I like to decipher. So if we take a look at example 1, we're going to look at some scenarios and decide whether the events in those scenarios are dependent or independent, and then explain. Okay? Okay, so if we look at A, it says a person pulls a red marble out of the bag that has 5 blue and 7 red, and does not replace it. Meaning they don't put it back in the bag. Then the person pulls another red marble. So let's take a look and see. Let's look at the probabilities. So the first pick, the probability, how many total marbles are there? There's 5 blue and 7 red. 12. Yeah, 5 plus 7 is 12. There's 12 total marbles. Of those, how many are red? 7. And what's 7 over 12 as a decimal? .58. About 0.58. That's the probability of getting a red on the first pick. Okay? They have a second pick. But there's the thing. They pulled a red marble out of the bag. They didn't put it back in the bag. They set it on the table or something. It's not in the bag anymore. So if we took one of those marbles out of the bag, how many total marbles are there now? Oh, there's 11. And how many are now red? 6. Because we took one of the red ones away. So now there's 6 out of 11 chance. And what's 6 out of 11 as a decimal? 0.55. So what happened to the probabilities between the first pick and the second pick? Yeah, it changed, right? So what do we say if the probability changes? Is it independent or dependent? Dependent. Yeah, that first pick, and by not putting the marble back in the bag, changed the probability of the second pick. Okay? Another good indicator of whether or not they're independent or dependent is what the action that takes place. Does not put it back in the bag. If you're ever seeing something like that, does not replace, does not put back, eats it, something along those lines, it's going to be a dependent event. Because by taking it away and not putting it back, you're changing the outcome of the second pick. Okay? By putting it, if they said, took a red marble out of the bag, knowing the outcome, put it back in the bag. Well, that would make it independent because by putting it back, you didn't change the outcome. It would still be 7 out of 12. Nothing changed. Okay? So it's a good indicator whether or not it's independent or dependent. So in this case, it's dependent. The probability changed. Questions over there? Well, if we take a look at B, it says a person flips a coin and notes that it comes up as heads. That's the outcome. Then the person rolls a standard 6-sided die and notes that it comes up as a number less than 3. Does flipping a coin have anything to do with rolling a die? No. If it lands on heads, does that affect whether or not you're going to roll a number less than 3? No. Okay? So would this be independent or dependent? Independent. They have nothing to do with each other. This would be an independent event. Probability doesn't change. The coin does not affect the die. Just because you're laying on heads doesn't mean you're going to land on a 1. But they don't affect each other. They're totally independent. Questions over that one? Okay. See, it says Owen picks an apple from a bowl of fruit and eats it. Then he picks a banana from the bowl and eats it as well. Are these dependent or independent? Yeah, why is it dependent? Yeah, very good. He eats the apple. So that's going to change the amount of fruit that's in the bowl, which means the probability is going to change on whether or not you pick another apple or whatever fruit you pick next. So we would say dependent. Owen ate the fruit. So it changed the probability. Questions over that? Again, trigger words for whether it's independent or dependent. Does not replace. Does not put back. Eats it. Those kind of things, that's telling you it's dependent because it's affecting the next thing. Okay. Questions over that one? The next one says, Chris picks a chocolate chip cookie from a jar, decides he doesn't want it, and puts it back. Chris then picks a sugar cookie from the jar. Independent or dependent? How did it happen? I think I do not like chocolate chip cookies. I think I'm the only person there that is all the time. Yeah! What did Chris do? What did he do with that chocolate chip cookie? Did he eat the cookie or did he put it back? He put it back. You didn't want it. Like me, I like chocolate chip cookies. So because he put it back in the container, in the jar, the amount of cookies remaining was still the same as there was in his first choice. Right? If there were 12 cookies when he pulled out the chocolate chip, he put the chocolate chip cookie back in the jar, there's still 12 cookies. It didn't change anything. Right? So this would be independent.
Yeah, but if he picks a sugar cookie back, it doesn't matter.
What if he picks a good chocolate chip twice in a row?
That's fine. It's not changing the outcome. But if there were 5 chocolate chips and how many, we'll say 7 sugar cookies. Okay? How many total cookies are there? 12. Okay? Yep. But there's 5 out of 12 that are chocolate chip. If you put the chocolate chip cookie back in the container, does the probability of getting another chocolate chip change? No. So the probability doesn't change for a sugar cookie because on the first choice there was still a 7 out of 12 chance that he can pick a sugar cookie. He put the cookie back in the container, so his second choice there's still a 7 out of 12 chance he gets a sugar cookie. The probability doesn't change for either type of cookie.
So it's the same amount of probability as
We're talking about between the first choice and second choice. If there was a third choice just between these two, the probability didn't change from the first to the second. So it would be independent. Nothing changed from the first to the second. Probabilities stay the same. Just think if he puts it back in the jar, independent. If he ate it, dependent. Don't worry about accidents. Just between the two things. So like event A is picking a chocolate chip. Event B is picking a sugar cookie. Those probabilities did not change going from event A to event B. Okay. Yes.
So if it doesn't tell you he ate it and you put it back?
It will tell you whether he ate it or he put it back. This is right here. He put it back. So it will tell you. Right. Other questions? So it's independent. Excuse me. You put the cookie back. So the probability doesn't change.
What do you not like about chocolate chip cookies? Just not your.
You know, chocolate.
I do not like chocolate chip cookies. I don't think they
Chocolate
make
in general.
But like M&M.
I do like M&M.
I love mini M&M's. I don't know why, but they're
I just chocolate chip cookies.
You might prove.
I do not like them. Not my thing. With the E, it says Mrs. Collini and Mr. Carr need 2 students to help them with a math demonstration for their geometry class. They randomly chose one student who comes to the front of the room. They then choose a second student from those still seated. Independent or dependent? Yeah, why is it dependent? Yeah, the student doesn't go back. So the population you're picking from, I think there's 25 of you in here. Okay? If I had one of you come up to the room, say Derek comes up, face Stan. So he comes up. We're now picking from another student. If there were 26 of you and Derek came up, how many students are there now? 25. So the probability change from your first pick to your second pick? Yes, you will. Think so. Okay. So yes, dependent. The student didn't sit back down. So the probability changed.
Where is Mr. Carr?
He's helping out with the OSC testing. That'll help. Help out with him. Right? Again, eats, doesn't put back, doesn't sit back down, does not replace, something along those lines is going to be dependent. If they put it back, or if it's 2 random things like flipping a coin and rolling a die, they're independent. They have nothing to do with each other. It's going to be an independent event. Just make sure you look for those kind of trigger words. There's a couple ways to test independence when given kind of word problems. One way is using conditional probability. Okay? It was on your quiz. So the conditional probability, you're given 2 events, A and B. If their conditional probability is the same as the probability of the first thing, if those 2 things are equal, those events are independent. Because B is not affecting the outcome of A. Because it's the same throughout. Nothing's changing. So that would make them independent. Same thing if you flip-flop them. If B given A and it's the same thing as B, then it's independent. Okay? Nothing's changing. Nothing is affecting the other. Okay? We can take a look at this in a word problem. I'm going to go ahead and write it on the top. Okay? So if this happens, those events are independent. Okay? If it doesn't happen, if the conditional probability is not the same as the probability of the first thing, then they're dependent, meaning B is affecting the outcome of A. So we can take a look at this. In this example, it says, does it appear based on the data in this table that the preference for math as a favorite subject has dependence on a student's gender? Okay. Well, we're going to see. We're going to see whether or not someone likes math given that they're a male. We're going to find that first. Okay? We're going to find the probability that someone likes math given that they're male. Okay? Then we're going to find the probability of the first thing, of just liking math. So we're saying, does being male affect whether or not you like math? That's essentially what we're finding. If they're the same, independent. If they are different, they are dependent, meaning male affects whether or not you like math. Okay? Well, this is just like what was on your quiz with conditional probability. Find the probability of both. So liking math and being male. How many like math and being male? 10. Then look at the second thing. How many total males are there? 27. And what's 10 over 27 about as a decimal? 0.37. Well, now, let's just find the probability of liking math. 18. Good. Out of what's the total population? And what is 18 over 57 as a decimal? 0.32. Are these the same? No. So does being male affect whether or not you like math? Yeah, it does. It affects it. These are dependent. If we got 0.37 for both or 0.32 for both, then that means being male has nothing to do with whether or not you like math. But because they're different, it does. Just based off this study. This is a hypothetical situation. Yeah, very cool. Well, let's see if it has anything to do with being female. So let's see. Does being female affect whether or not you like math? Doing the same thing, right? Conditional probability, and then if that's the same as just liking math, which we already found was the probability of liking math, 0.36. So they're the same. Being female has nothing to do with whether or not you like math. If they're different, then it does. Okay? We'll look and see. Both. How many are female and math? 8. Look at the bottom. How many total females are there? 30. What's 8 over 30 as a decimal? 0.27? No. So there is some sort of effect. Being female does affect whether or not you like math. Okay?
Is this accurate?
This is just hypothetical. I like math.
I'm a math is bad.
Yeah, I'm there. Yes.
And I like science.
If the probabilities are so dependent, it's dependent, but if it's
Independent. Yep. So both of these are dependent. Your gender affects whether or not you like math. Just based off this particular study. Okay? So dependent because the conditional probability is not equal to the probability of first. So your math showing that these are different is your work. You just say dependent, gender, affects, something along those lines. Okay? Well, let's see it for the same thing. Let's see if your gender affects whether or not you like social studies. Same exact steps. We're first going to find whether or not being male changes whether or not you like social studies. Are they somehow related or have nothing to do with each other? So again, conditional probability. Look at both. How many are both male and social studies? 9. Good. Out of how many total males are there again? What does 9 over 27 reduce down to? 33%. 0.33, or 1/3 as a fraction. Well, oh, that's what you're supposed to study. Thank you. Probability of the first thing. We're not dealing with math in this one. Okay. Well, let's find the probability of liking social studies. How many total people just like social studies? 19. Out of 57, the total population. And what is 19 over 57? as a decimal? 0.33. So are these independent or dependent of each other? Independent, yeah. Being male has nothing to do with whether or not you like social studies. There's no connection there. Okay? Now, that might not be true in the real world. I don't know. This is hypothetical. Based off this data. Oh, look at this. There's no effect. Okay. Well, let's see if it affects female. So we're going to see probability of liking social studies given that you are a female. Same thing, conditional probability. How many are both? Social studies and female. How many are both? 10. Out of how many are just female again? 30. And what is that as a decimal? 3. Well, again, probability of just social studies we said was what? 0.33. So in this case, gender does not affect social studies. Apparently only affects math. Okay. So they're independent of each other. Gender does not affect social studies. Because they're the same. Nothing. The gender is not changing the outcome of liking social studies. And A, gender was changing the outcome of liking math because they weren't the same. That's essentially what you're trying to find. Okay. Questions over that? That's one way to test using conditional probability. There's another way you can test for independence is the product test. Okay? Meaning if you multiply two probabilities together and it's equal to the probability of both things, their intersection, then they're independent. If you were to multiply two probabilities together and they are not equal to their intersection, then they're not independent. Okay? They're dependent to each other. One, they affect each other. Okay? So again, and you'll be told use product test for independence. That's it. And when you do that, you're using this little formula. You're seeing if their intersection is equal to their product. Okay? So we take a look at example 3. It says the probability that a person is left-handed is 12%. The probability they have brown eyes is 42%. And the probability they have brown eyes and are left-handed is 2%. Is the event of having brown eyes independent of being left-handed? When you have these percentages and you're asking if it's independent or dependent, that's also an indicator, hey, I'm going to do this. Okay. So what you're going to do, you're just going to multiply the two probabilities together, and it should equal, if they're independent, the probability of both. Okay. So the two things we're dealing with are what? Being left-handed and... So we have left-handed and brown eyes. Okay. Well, what's the probability of being left-handed? 0.12. What's the probability of having brown eyes? 0.42. And if they're independent, they should equal both. Left-handed and brown eyes. Okay. Well, what's the probability of both being left-handed and having brown eyes? How do you write 2% as a decimal? 0.02. It should equal that if they're independent. Well, multiply 0.12 times 0.42. What does that equal? 0.05. That equal 0.02? No, they do not equal each other. Okay? That's your justification doing that work. Right? So we would say, no, these are dependent. Because they're not the same. Meaning, having being left-handed is going to affect whether or not you have brown eyes. Or having brown eyes affects whether or not you're left-handed. They're affecting each other. Right? Depending on the take a look at the next one. So the study was done to find the effects of hearing on teenagers who listen to loud music through their headphones. 70% of teenagers in the study listened to loud music, 52% had hearing problems, and 32% of the teenagers had both hearing problems and they also listened to loud music. Is listening to loud music independent of having hearing problems? Okay. Well, what are the two things we're dealing with? What two things did they study? Loud music is the first thing. Times the second thing is hearing. And if they're independent, it should equal both. Music and hearing problems. Okay. Well, what's the probability of loud music as a decimal? 0.70. Just put the decimal point right out in front. What's the probability of having hearing problems as a decimal? 0.52. And then what's the probability of both as a decimal? 0.32. We'll multiply them together. 0.70 times 0.52 is what? So about 0.36. Does that equal 0.32? They're not equal. So are these independent or dependent? Dependent. Meaning listening to loud music affects whether or not you're going to have hearing problems. If you got 0.32 equals 0.32, that means listening to loud music has nothing to do whether or not you have a hearing problem. There's no connection there. There's no relation. One more. Since two events A and B are independent, if the probability of A is 0.4 and the probability of A and B is 0.32, find the probability of B. Well, if we know that these events are independent, we know they're independent. What do we know about their product? Product is going to equal, you're on my track. The what? Yeah, the product is going to equal their and. It's going to equal 0.32. So using that formula, the probability of the two things multiplied together, if they're independent, will equal the probability of their intersection, their and. Okay? Just like we did in those last examples. We multiply the two things together. If it equaled their and, they were independent. If they didn't equal the and, they were dependent. But in this case, we know they're independent. So we know it's going to equal 0.32. We know it's going to equal the and. And we know that the probability of A is 0.4. We don't know the probability of B. That's what we're trying to find. So what do you think we have to do with that 0.4? Yeah, just divide. Just solve it like a normal equation. Just divide by 0.4. That's canceled. What's 0.32 divided by 0.4? 0.8. So the probability of point B is 0.8. So sometimes you might have to go a little backwards with that. Questions over that?